since I know that y'all know a little bit about a deck of cards, hopefully this won't take as long as it does some years when I have classes that know nothing about a deck of cards. Yep, 52 cards in a deck. We've got...
Not including the jokers?
Correct, yeah. Well, pretty much for everything, we'll say not including the jokers. Like, it's never going to tell you to include them. There's 4 suits. You don't really have to know what they are, but there's 2 black, 2 red. So there's 26 of each color, 13 of each suit. Face cards, obviously, are Jack, Queen, King. And then you've got, you know, Ace through 10 or whatever. Or I guess 10. Is there a 10?
Yeah.
Yeah. I was like, wait a second. Now I have to question it. I think there is. I don't know. Anyways.
Yeah.
But there's 13 of each thing, but that's not really relevant. They're never really going to ask you, like, oh, draw in a number 7. Like, it's going to be, like, typically a face card or maybe an ace periodically or something like that. So, you have a standard deck of cards. Find the following. 1 card is drawn. Find the probability that it is an ace or it's red. Okay? So, there's 26 red cards, 26 black cards, but it says ace or red, right? So that means that it could be red, which would be 26, and ace. There's 4 aces, but
2 of them are red.
yes, 2 of them are red. That's that overlap we're going to be subtracting off. So we have basically it is I don't know why I have this written this way, but 26 over 52 plus 2 over 52 because we've already accounted for it. If we did it the other way, which is the new way, I'll do that separate in just a minute. But this would give us 28 over 52. Is 0.538. Now, the other way, if we didn't think it through that way or whatever, if we wanted to do it differently, we could have also done, okay, there's 26 out of 52 that are red, plus there's 4 out of 52 that are aces, and then I've got to subtract off that middle amount, remember that overlap, which would be that there are 2 that are in both, and I would have still gotten 28 over 52. So when you kind of just know, you don't really have to use the formula. The formula more comes in when it's stuff that you don't just know, or if they're giving you decimal numbers and stuff that you're dealing with.
At least one we could do the little circles with.
Yeah, so we could,
So it would just be if you're taking 2 out of both, would it be 24 on one side, and then
Yep.
would it be? Wait, what would be on the other side?
well, both sides would be 24, because there would be 24 that aren't aces on red and 24 on black, and then there would be
The 2 overlap.
4, because it'd be 4 total aces.
Oh, okay. And then it would be 24 right there.
Well, 24, 24, and 4.
Yeah. Okay.
Yeah. This one, yeah. There are going to be some that we're going to want to draw the diagram. This one, you don't really need it, but... So 2 cards are drawn without replacement. So that means I take 1 card and I don't put it back in. So find the probability that both cards are aces. Okay, so the first one, the probability that it's an ace is, 4 out of 52, because I have 4 aces out of 52 total cards. Now, because I'm looking for a both situation, in 2 cards, then the next one, it's without replacement, so I have taken 1 card and removed it. Okay, so it's going to be out of 51. Now, I had pulled an ace the first time. How many aces are left in the deck? 3. So this is going to be 3 over 52 times 4 over 52 times 3 over 51. So 4 times 3 divided by 52 is .0045. So essentially less than a 1% chance that occurs. Less than a 0.5% chance, technically. All right, 5 cards are drawn without replacement. Find the probability that all are spades. Okay, so how many spades are there to begin with? 13. So the first one's going to be 13 out of 52. Now we're drawing 5 cards, and we need that they're all spades. So it's going to be 13 out of 52 times, we've removed 1 spade, and we've removed 1 in total. So 12 out of 51 times 11 out of 50 times 10 out of 49 times 9 out of 48, because I'm removing a spade every time and thus removing a card every time. So this one ends up And so you have to watch, because the calculator, when it gave me the answer, did 4.95 times 10 to the negative 4. But we don't leave answers this way in stats. We would need to write it as 0.000495 for us to do it like that. So we don't want answers in scientific notation when we do it. All right, so these next 2 are conditional probabilities. So 1 card is drawn. Find the probability that it's a heart, given that it's red. Okay, so on top, or maybe as a refresher here, I'll write this. This is going to be the probability of heart intersected with red. So basically how many red hearts there are out of the total number of red. It's whatever the second thing is listed, so the probability of red. All right, so how many are red hearts, basically?
13.
Yep, so 13. So that'll be the number on top. Out of how many cards are red?
26.
So 13 out of 26 reduces to 1/2, or 0.5. So now in E, we're going to do the reverse. We're going to do the probability that, I don't know where the P's missing, but the probability that it's red, given that it's a heart. So that's going to be the probability of red intersected with heart, which is going to be the exact same thing on the top that it was in the previous problem. No matter if we write red or heart first in the intersection, it doesn't matter, because it's just where the overlap is. Out of the probability of heart this time. So red heart was 13. Out of, there are 13 hearts, which is just 1. So basically, the probability that it's red, given that it's a heart, well, if it's heart, it has to be red. There's no other option. So it's basically like 100% chance that that's the case. A little bit of a drastic example, but. All right, 1 card is drawn. Find the probability of red or face card. So the probability of red is what?
26 out of 52.
Yep. I don't know why I was going to do that. So 26 out of 52. Plus, what's the probability of a face card?
12 out of 52.
12 out of 52.
Yep. 12 out of 52. Now, how many face cards are red?
6.
So we're going to subtract off 6 out of 52. So that ends up giving us 32 out of 52. Or 0.615. So this is using the probability rule where we're like obviously subtracting off that overlap part. One card is drawn, find the probability of red and a face card. So basically, how many face cards are red?
6.
Yep, so this is going to be 6 out of 52, which is 0.1154. All right, so the addition rule and the multiplication rule, I'm going to write them out for basically if there's overlap and then if they're disjoint, just so that we have both as a refresher. So addition is when we see the word or you see something like the U for union. We're using the addition rule. So this is the probability of A union B is equal to the probability of A plus the probability of B minus the probability of A intersect B. So this is when there is overlap. If A and B are disjoint, meaning no overlap, then obviously I don't have to subtract off anything. It is just the probability of A union B is equal to the probability of A plus the probability of B.
What's that like thing with the minus in the middle? Like,
This one?
uh,
Intersection.
okay. It's just like kind of like an upside down U.
Yeah. I try to look at it like to keep in mind like union, obviously it looks like a U. Intersection, I'm like in intersection, so I'm like it kind of looks like an N, like the people, like the cursive N's that just have the one hump to them. When people do them like this, technically it just has like the one hump. I kind of try to think of it like that to help me keep them straight of which one's which. So the multiplication rule is for and. If you see the word and, think multiplying, and then it's the little upside down U for intersection. So the multiplication rule says the probability of A intersect B equals the probability of A times the probability of B given A. To see, I have a feeling it's going to be written in here somewhere, but maybe not. I guess not. So, just because I don't think it's written in here anywhere, the probability of B given A is equal to the probability of B intersect A over the probability of A. So this is like our general multiplication rule, but if A and B are independent, the probability of A intersect B is equal to the probability of A times the probability of B. So if we know they're independent, we can do it that way. How many pages of examples do y'all have? I thought I only screenshot 5 pages, but I have 6 pages up here in my
Five.
Wait,
printed.
Yeah.
Okay. Something might be missing. I'm not sure. We'll figure it out when we get there.
What was the formula in red?
That's the, like, B given A.
Oh.
I just, like, rewrote, or, like, wrote that out. Which it should make sense because the probability of A times the probability of B intersect A over the probability of A would just be equal to the probability of B intersect A when you cancel. So something I like didn't really have that realization like of for a while, and I like kept trying to figure out like how to like keep the formula straight and stuff. So
Wait, so that's like the reverse of it, or like?
no, it's just that written out in actual form.
So it's just the same thing.
Mm-hmm.
Okay. Do you use them in like different scenarios though, like different situations?
Yeah, sometimes
Okay.
they'll give you, like they'll tell you the probability that it's red given that it's a heart, or well, it's a heart given that it's red. They might give you that probability,
Okay.
and they might tell you the probability of it being a heart, and then you could find the probability of the intersection by that formula. Then
So it just depends on how it's worded. like,
yeah,
which one you-
and kind of what they give you.
Okay.
All right. Employment data at a large company revealed that 72% of the workers are married, 44% are college graduates, and half of the college graduates are married. Okay? So they don't explicitly tell us the number of college graduates that are married, but if it tells us that it's half, how many is that?
50%.
Nope, half of the college graduates are married.
Wait.
22%.
Yeah, so this
Oh,
is 22% are essentially married grads. All right, so first thing is to draw a Venn diagram to represent this situation. So you usually start out by drawing like the big box. And then I'm going to draw 2 circles inside of it. Almost left enough room in there to draw something in it. Good enough. Need to like bring the brightness down so you can actually see it. All right. So we know that 22% are married and graduates. So that's going to go in the middle. Now, 72% of the workers are married, but we have to take off the 22% that are also college graduates. So that means that there are 0.5 that are just married. Then 22% of the college graduates are married, so the rest of them are another 22%, so 0.22 that are college grads.
Wait, how did you get 0.5?
0.72 minus 0.22.
Oh, okay. I was thinking like the number 5.
Oh, no.
That'd be like
Yeah.
0.05, never mind.
All right, so then the other thing to make my Venn diagram complete would be to figure out basically who's not married or a college grad. So, I would add up the numbers inside, so 0.5 plus 0.22 plus 0.22, and then subtract that from 1, and what would I get when I do that? .06.
Oh yeah.
So .06 are the ones that are neither, which I think just answered question B. It happens sometimes. But the more you can put into your Venn diagram, oftentimes you can use that to help you answer your questions as you go. So, what's the probability that a randomly chosen worker is neither married nor a college graduate? So that's the complement of what's in the circles, which is .06. If you want just for reference, you can do 1 minus 0.5 minus 0.22 minus 0.22, which gives you .06 if you need that for reference for how we got that. Just gonna draw an arrow to that. What is the probability that a randomly chosen worker is married but not a college graduate? So again, we've got that already in our Venn diagram because we did that first. So just married, not a college graduate. That means not the part that's in the intersection between the two things. So that's going to be 0.5. Now, with question D, there's going to be two different ways we can do this problem. And this is where we have to pay really close attention to what we're doing. What's the probability that a randomly chosen worker is married or a college graduate? Okay, that means anything inside the circles. So we can either, because we have the Venn diagram, add up all the numbers in the diagram, or we can use the general probability rule. I will do it both ways so that we have it using the addition rule. So by just using the diagram, we just add up all these numbers. So 0.5 plus 0.22 plus 0.22 is 0.94. Or even a third way is we could do 1 minus the probability that they're neither, and we would also get it that way. If we use the addition rule, what we would do is we'd use the original numbers that they gave us. Okay? So we would add 0.72 plus 0.44. But then we've got to subtract off the intersection where it said half the college graduates are married. So I've got to subtract off 0.22. And when I do that, I'm still going to get 0.94. So either way we do it, I'm going to get the same thing. But you just have to remember that if you're using the diagram, we're not subtracting off the middle part. Okay? That's the key part where people tend to get confused. So just know which way you're doing it. I don't care which way you're doing it unless for some reason the instructions specify. But you should make sure you know the probability rule because that's probably more likely to be obviously how they would write it on the AP exam if they're writing answers out and stuff. All right, independence. Two events A and B are independent if probability of A is equal to the probability of A given that B has already occurred. So that's just saying that essentially B already occurring makes no difference to the final thing for them to be independent. All right, 56% of all American workers have a workplace retirement plan, 68% have health insurance, and 49% have both benefits. Draw a Venn diagram to represent this situation. So, just because these words are kind of long, and when we do our Venn diagram, I like to put labels as to what each circle represents. I would say for a retirement plan, I would just use RP, and for health insurance, I would use HI, just for ease, but just specify, if how I just did, if you're going to use an abbreviation or something, just specify so that I can tell, when I'm grading something, what's going on. All right, so we have 56% have workplace retirement plan, 68% have health insurance, and 49% have both. Draw a Venn diagram to represent this situation. So I'm going to set up my box again. All right, so it's always best to start with both, which is the 0.49. And then I'm going to do retirement plan over here, health insurance over here. So, how many just have retirement and not health care or health insurance? 0.07. And then how many have insurance and not both? Or not, sorry, insurance and not retirement?
1.9.
Yep, 0.19. And then how many don't have anything?
25 or 0.25.
Yep. Which again is going to happen to be question B. If a worker selected at random, what's the probability that he or she has neither health insurance nor retirement plan? So 0.25. So everything outside of the box. All right. If a worker is selected at random, what is the probability that he or she has health insurance if he has a retirement plan? So basically that's the given that they have a retirement plan. So we would write this as the probability of health insurance given retirement plan. The formula is the intersection of the two things. So the probability of health insurance intersected with a retirement plan over the probability of the second thing listed, so the probability of a retirement plan. So the intersection of those things is 0.49. That's how many have both. Out of the probability that they have a retirement plan. Now, that's the total for the retirement plan. That's not saying retirement plan that doesn't have the other. That's just saying out of retirement plan. So that's the 56%. Now, I guess I should specify this is actually 49 out of 56, not with the decimals. If you put the decimals, you're going to get a weird answer. So this gives us 0.875. You just get some extra zeros in there if you divided it. So, all right. So I'm gonna see if you understand the meaning of mutually exclusive. Are having two benefits mutually exclusive?
Wait, what does that mean again? That would be like.
That's what I'm trying to see if you know.
Yeah. Okay.
No.
Why?
Like, would the probability, like, be equal?
That's for independence.
Oh. Yes.
Is
Wait.
there overlap?
Yeah, so
Yes.
it can be mutually, like it could be, but it doesn't have to be, right?
No.
Okay.
You can't be mutually exclusive and have overlap.
Oh,
So, no, there's overlap. 49% have both. All right, so are having health insurance and a retirement plan independent events? So anytime that I have a problem that like continues down like this, I try to use something I have already used before or I've already found. So I've already found a conditional probability for the probability that they have health insurance given that they have a retirement plan. So up here, two events are independent if the probability of A is equal to the probability of A given B. So based on that, health insurance given a retirement plan should be equal to the probability of health insurance if these things are independent. So I'm going to find the probability of health insurance and see if it's equal to the probability of health insurance given a retirement plan. Now, in this case, the probability of health insurance given a retirement plan I found was 0.875. What is the probability of health insurance?
0.68.
Yep, 0.68. Are these things equal?
No.
not equal, I usually just put a slash through it. And then I will say something along the lines of not independent. And then something like if someone has a retirement plan, they are more likely to also have health insurance. Did y'all get all that? All right. See if we can at least get through this one. The soccer team shirts have just arrived in a big box, and people just start grabbing them, looking for the right size. The box contains 4 mediums, 10 large, 3 extra large. You want a medium for you and one for your sister. Find the probability of each event described. So, what's the probability that the first 2 you grab are the wrong size? And we're going to assume without replacement, because if you're looking for a shirt and you take one out and it's the wrong size, why would you put it back in before you find the one that's right? Okay? So it doesn't explicitly say without replacement, but we are going to assume that we would not be throwing that shirt back in the box at this point.
I look, you might do that.
I thought I would.
All right, so how many shirts are there total?
So 20?
20. All right, so the first thing's going to be out of 20.
16?
Yep, so 16 are the wrong size, so 16 out of 20. Now, we're multiplying because it's like the first 2 that you're taking are wrong, so times, what would the next thing be?
Also 16 out of 20?
Without
15.
replacement.
Oh,
15 out of 19.
15 out of 19, that's why it's critical to know that. Now, I'm going to tell you, if y'all didn't say without replacement, if I don't specify on the quiz or something and you do, you do it the other way, I will still give it to you. But this should be something that's without replacement. Like, if you pull the wrong card out of the deck, you're not going to stick it back in there and do that. So this is going to end up being 0.63. All right, how about the first medium shirt is the third one you check? What do you think we would need for this one? Or what does that mean about the first 2?
They're wrong.
They're wrong. We've already found that number. Now, I'm going to write it out again just for visual because obviously you may not have always had what's before. But we already know what that number is. And then times,
4 out of 18?
yep, 4 out of 18. Because there would only be 18 shirts left in the box and 4 of them are correct or would be the right size. So this number is going to be 0.14. All right, now the first 4 shirts you pick are all extra large.
So 6 out of 20, and then just like keep going.
6 out of 20, 5 out of 19,
Yeah.
4 out of 18, 3 out of 7.
Yep. And that number is going to be 0.003.
It keeps like being the same problem, and it just adds like one more thing on.
Pretty much. All right, this one is a little different though. At least one of the first 4 shirts you check is a medium. Do we care which one? No. So, I'm going to do, we see at least one. What do you think that means? Okay, right. But what do we use when we see the words at least?
Oh, I know. Wait, hold on.
What's the
Oh,
word?
the complement.
Yes. So I'm going to do 1 minus the probability that none of the first four are medium. So this is going to be 1 minus the probability, or not the probability, 1 minus 16 out of 20, because that would be a wrong size, times 15 out of 19, times 14 out of 18, times 13 out of 17. So that would be that none are medium. 1 minus that, because we could have 1 that's medium, 2, 3, or all 4 that happen to be medium. Now, obviously going to be a very low chance that the first 4 I pull are medium, because statistically that's just not going to happen. But when I do this and I do 1 minus that, I get 0.62. So basically, there's a 62% chance that if I pull 4 shirts, one of them is going to be a medium. Let's look at the first part of this. I don't know if we'll get this whole problem in before the bell rings. It's not super long, but the probabilities that an adult American man has high blood pressure and or high cholesterol are shown in the table. So we have where both things are high. We have where one is okay, one's high, vice versa, and then where both are okay. So what is the probability that a man has both conditions? So this is just looking at the table and answering it.
111?
Yep. 0.11. What about that a man has high blood pressure?
Point.
Point 2, 7.
Yep, so you add
Okay.
0.11 plus 0.16, which gives you 0.27. All right, a man with high blood pressure has high cholesterol. So this is the probability of high cholesterol given that they have high blood pressure. So this one is weird because they actually wrote it backwards. Okay, a man with high blood pressure, we know that he has high blood pressure, so that's going to be the given, that part, has high cholesterol. So that's the part that goes first.
So, wait.
So the intersection of the two things is 0.11, which we would need to write as 11 or it's going to give us a weird decimal. So it's going to be 11 out of the probability that they have high blood pressure. We already found that is 0.27, or we'll need to write it as 27 for it to give us the correct decimal here. And that's going to give us 0.41. Now, they are going to flip it on us. A man has high blood pressure if it is known that he has high cholesterol. So we know that he has high cholesterol, so this is just flipping it. So this is going to be the probability of high blood pressure given that he has high cholesterol. So the probability of the intersection of the two things will remain the same. That's going to be 11 out of the probability of high cholesterol. What's the probability of high cholesterol? Because we have not found that yet.
0.32.
Yep, 0.32. And you could fill out all the totals when you first get this if you were so inclined. But yes, 0.32, or we'll call it 32. And that's going to give us 0.34.